Hello class, today we're going to be looking at covalent bonding. We've looked at ionic bonding and ionic compounds, and we've compared the properties of the two different types. We saw solubility was one property that distinguished the two different types of compounds. Ionic compounds tended to be more soluble, although not always the case. Some molecular acids and even some organic compounds such as sucrose were very soluble, and even the ionic compounds tended to have solubilities which varied quite a bit. We saw hardness varied a little bit between the two different types of compounds. Some ionic compounds were very hard, some were relatively soft, but it depended on the form. And also melting point. In that case, that property seemed to suggest that ionic compounds have relatively high melting points, whereas molecular compounds such as menthol or citric acid had relatively low melting points. So that suggests a weaker bond in the case of the covalent molecules or molecular, and we'll try to understand why that might be the case as we explore this topic. So first question is, what is a covalent bond? I'm just going to reveal the points that are on your note. Molecular compounds are the type that contain covalent bonds, and they're called molecular compounds because the particle can be called a molecule. It's not ionic, it's not a formula unit, it's a group of two or more non-metal atoms bonded together. Now the nature of the bond is different as well from ionic, whereas we had transfer of electrons from metal to non-metal atoms. In covalent bonding we have a sharing of electron pairs, which forms a strong attractive force called a covalent bond. And keeping in mind, both atoms are trying to achieve typically a stable octet, a complete valence complement of electrons. So the nuclei of each atom has an attraction for electrons, and when the attractive forces can interact, where electrons can be shared between the two valence orbits, then a covalent bond is formed. When one atom has much stronger attraction for electrons, then it's most likely to gain those electrons, or we could say steal them, from the other atom. And we'll look at this a little bit later on in the chapter with the bonding continuum. But for now, a covalent bond is a sharing of a pair or pairs of valence electrons between nonmetal atoms. There's a couple video clips here which will help you to appreciate this point.
Atoms have three distinct electrostatic interactions with each other. The electrons repel. Similarly, the nuclei repel each other. Finally, the electrons on each atom are attracted to the nucleus of the other atom. When this attractive force is greater than the combined repulsive forces, a chemical bond forms.
All right, well that illustrated the reason why a chemical bond forms. It has to do with really the balance between atoms pushing each other away and atoms drawing closer towards one another. All right, and some of these concepts that are being introduced here are going to extend into grade 12. So I'll show one more clip for the 4C students. Feel free to pass over this, but exothermic and endothermic are terms that relate to thermochemistry and the study of energy involved in chemical reactions. This introduces a bit of a connection to that field of chemistry, specifically with bond formation. So we'll show another one here.
Hydrogen and chlorine react to form hydrogen chloride. Because the total energy of the broken bonds is less than that of the bonds formed, the overall reaction is exothermic.
All right, moving on. Now we're looking at trying to determine the number of bonds that are formed. So if it's pairs of valence electrons, can't be a single electron, because that would only satisfy the valence orbit of one of the atoms. So both atoms are usually involved in providing you could say the raw materials or the resources for the shared pair. There's an exception we'll look at, but it always involves a pair of electrons. And octet, stable octet is still, here's something that we want to keep in mind. A full complement of valence electrons is what generally achieves stability for an atom. And we want to refer to this concept called a bonding capacity. So in your gizmo that you explored, you went and looked at the number of valence electrons in different nonmetal atoms, the number of electrons that were needed, which was called the valence, and now that can also be referred to as the bonding capacity, which makes a little bit more sense when you look at the two different terms, the capacity to bond and how many bonds it can form specifically. So that is the definition for bonding capacity. In your textbook on page 77, you'll see some information about the summary of bonding capacities for some common nonmetal atoms, and here the relationship between the number of valence electrons, the number of bonding electrons, and the bonding capacity should be pretty evident. The number of bonding electrons is equal to the bonding capacity, and the bonding capacity would be equal to 8 subtract the number of valence electrons. And that's a simple rule that you can use. If you go to a periodic table and you look at a periodic table, you can look at the group number, and that's another way of determining the bonding capacity. Strictly looking at nonmetal elements here. So for example, group 4 elements have a bonding capacity of 4. They have 4 valence electrons. They need 1, 2, 3 more to become similar in an electronic arrangement to the noble gases. If you were to look at group 5 elements here, they have sort of 3 hops to get to the nearest noble gas, meaning they would need 3 more electrons. And if they're sharing electrons, then they can share a pair with another atom or atoms. And if we were to look at group 6 elements, they're just 2 away from having a full octet, and so they'll have a bonding capacity of 2. They'll need to form 2 bonds or 2 shared pairs of electrons. And finally, if we were to consider the halogens, the group 7 elements, they're just 1 short from a full octet, so they'll have a bonding capacity of 1.
One or more atoms may share electrons, thus forming a covalent bond. Electrons will spend a portion of their time associated with each of the participating atoms. A single covalent bond represents the sharing of 1 pair of electrons, such as with 2 hydrogen atoms. A double covalent bond is formed by the sharing of 2 pairs of electrons. Atoms sharing 3 pairs of electrons form triple covalent bonds between.
Okay, moving on. Again, the point we want to look at now is that, as was mentioned before, a covalent bond is a force, and we can appropriately call it an intramolecular force. There are 2 different types primarily of forces. There are intermolecular forces, which are between molecules, and those determine properties such as melting point, boiling point. But intramolecular forces are the forces that hold the molecule together. The covalent bond is an intramolecular force, and its strength is determined by the extent of sharing. So a triple bond has 6 electrons or 3 pairs which are shared. You could almost think of the atoms, they've got more invested in the bonding, and so it's going to be much stronger relatively compared to double bonds with 2 pairs of shared electrons and single bonds with only 1 pair of electrons. So make sure you're clear on the fact that number of pairs equals the number of bonds, but the number of electrons is, of course, twice that amount. So there'd be 2 electrons involved in a single bond, 4 electrons involved in a double bond, and 6 electrons involved in a triple bond. All right, as always in chemistry, because it's such a subject with abstract ideas, things that we talk about and we reason through, but we don't see directly, we need to have a way of modeling bonding or modeling the structure of a molecule. It needs to be visual. So a Lewis structure is sort of a continuation of the Lewis symbol, which we use for usually individual atom or an individual ion. A Lewis structure and a structural formulae are not quite the same thing. One shows bonded pairs, which are the shared electron pairs, as lines. and non-bonded pairs of electrons are shown as we would in a Lewis diagram as dots, and the symbol of the element is central. With only bonded electrons shown, those would be the single bond or the double bond or the triple bond shown, we would call that a structural formula, which just shows the way in which they're connected by bonds. The Lewis structure is probably preferred because it allows us to count all the electrons around the atom and ensure that a full complement of usually 8 of electrons per atom is present. Structural formula is more used when we're just trying to show the connectivity and possibly even the shape. The rules for drawing Lewis structures and structural formulas are pretty detailed. It's in your textbook on page 79, and there's also a handout given here which outlines many steps that in most cases are needed in order to determine the Lewis structure or the structural formula for a given compound. So read through this series of steps, and the example shown is for sulfur trioxide. And when you're familiar with it, we're going to attempt to go through some examples together, which you're also going to fill in on your handout. I think as you read through these steps, it seems very procedural. It seems to suggest that there's a lot of things you have to keep in mind when you're drawing a Lewis structure. The one objection I have to this whole method is it sort of strips off the electrons from the atom and then sort of puts them back on as it suits the situation, achieving full octet usually as the goal. But my preference is really not to look at total number of electrons to begin with. Of course, you do have to be aware that if you have a charge on your particle, then additional electrons have maybe been added or removed from the total. So that does need to be considered at some point. However, if you follow through the steps in this process, valence electrons only are important. So that's really key. So when you're drawing your Lewis symbols to begin, you're not only showing valence electrons. Obviously, you're combining two atoms together to make a bond using a pair of electrons, so that's consistent with what a covalent bond is. When you look at where the elements are, or where the atoms are arranged, how they are arranged, the first point is has some good ideas here, that the central position is the element that has the highest bonding capacity. So in the case of sulfur and oxygen, they both have a bonding capacity of 2, but there are 3 oxygen atoms in the molecule and only 1 sulfur. So it would be reasonable to put the oxygen atoms around the other element. If you look at the remaining steps from 4 down, it's a method which personally I don't prefer. And I'll demonstrate in a minute why, and the method I prefer. But you may relate to this, and it may seem to work really well for you at first, and then maybe after some experience has been built up, you may find that you can combine some steps, and you know to check for certain things as you go along. You always looking for complete octets for all the elements, and only then can you really consider the Lewis structure to be complete. I will talk about coordinate covalent bonding a little bit. The 4C class, you can skip over that for now, and if some of the examples relate to coordinate covalent bonding, again, that's not a requirement for your course, so you can also pass through those. The final test is, do all of the atoms have full octets? And if we want to look at the finishing product here, which is almost there, we would just count the number of shared pairs of electrons, and the difference between those two is that this would be more closely resembling the Lewis structure, and this would be the structural formula, where we have no peripheral electrons. So the structural formula is shown here with 4 bonds to the sulfur, giving it 8 electrons. But what's not shown in the structural formula is really what the Lewis structure would show, which is that each of those oxygen atoms has 6 non-bonded electrons, with the exception of this oxygen atom over here, which has 4. And again, if we count the number of electrons, we should get 8 around each atom. Okay. In this case, if we were to look at fluorine, fluorine has 7 valence electrons and there are 2 of them. So we could take the approach that there are 2 times 7 equals 14 valence electrons. We could place fluorine side by side, and we could start attempting to, as the method says, put pairs of bonding electrons together as a shared pair, surround the elements with the remaining electrons. And in that case, that would give us 6 and 6 is 12, and 2 shared is 14, so that would give us a predicted single bond, which would have a structural formula as shown, where we are omitting non-bonded electrons. That method, in some cases, isn't necessary. What I would do, rather, is I would start with the Lewis symbol for both elements and just look for, using the bonding capacity, a quick way of sharing the electrons to achieve full octet. Let's say, for example, we apply that method for hydrogen and oxygen. Now, hydrogen has a bonding capacity of 1, and oxygen has a bonding capacity of 2. So here we're going to place our central atom in the middle, which would be the oxygen. And if we draw its Lewis symbol, we can easily see that in order to achieve a full octet for oxygen, we would have to share an electron with this hydrogen atom and another pair shared over here. Hydrogen is not seeking to achieve a full octet. It's stable with a complete first orbit with 2 electrons, and it now has that. And so our structural formula for water would look something like this. We're not concerned too much about the shape at this point. Grade 12 4U course focuses on bond angles and the shape of molecules, but for now we're just looking at representing lines to show shared pairs of electrons. So that would be the structural formula for water. Now at this point, what I would suggest you do is try most of the examples on this page and return to the video when you have exhausted your efforts or you think you've been able to complete them all, and then just compare answers. Okay, well, I've actually left the Lewis structure diagrams for now, and I'll just go through each one. We did water, we did fluorine gas, this diatomic molecule. Looking at methane gas, the state of matter isn't really relevant here, but I just included it to help you make some connections between the molecule itself and the most common state at room temperature. We have in carbon's case 4 as a bonding capacity and 1 for hydrogen, so we would predict 4 single bonds. There are no peripheral non-bonding electrons here because hydrogen only has 1 electron and now it's sharing a pair. So that's both the structural formula and the Lewis structure. Phosphorus trichloride has a central atom of phosphorus because of its bonding capacity of 3. Chlorine is 1. I'm not showing any peripheral non-bonded electrons on chlorine, and I'll just remove at this point the 2 non-bonded electrons on phosphorus. There's a structural formula. We have to be careful when we first start representing molecules that you do the structural formula last, because if you count the number of electrons at this point, you would see 2 for every line. May lead you to think that there are only 6 electrons surrounding phosphorus and only 2 surrounding each chlorine atom. So if you prefer to draw the Lewis structure, I would encourage you to do that. But for this Lewis structure here, double bond for dihydrogen sulfide and removing non-bonded electrons. For silicon dioxide, we would have 2 double bonds, giving silicon, the central atom, 8 electrons, and each of the oxygens would still have 8, 2 non-bonded and 2 bonded pairs. Looking at hydrogen gas, which is also diatomic, no non-bonded electrons, single bond. I'm going to skip over 2b for now. Oxygen difluoride would be, again, central atom is the oxygen, two single bonds, and a lot of electrons to remove here for the structural formula. All single bonds. Looking at nitrogen trifluoride, it would be a lot like ammonia gas, NF3 now, instead of NH3. Three single bonds to the central atom, nitrogen, and fluorine rather, only needing one additional electron, shares one pair with the nitrogen atom. Our last two examples here, again, the length of the line is not really that important, and how exactly it's connected is not really crucial. Might want to redraw them to make it a little bit neater here. Probably this would be a little bit more easy to look at. And again, a couple electrons that we need to remove here. And the last example is diphosphorus tetrahydride, which has two phosphorus atoms. Both have the same bonding capacity, but it's more than hydrogen, so that suggests that they're towards the center of the molecule. Hydrogen only needs one bond, so it has to be towards the outside. Phosphorus needs to make three, and in fact it does. A double bond and a single bond to each phosphorus atom. Now, for the 3U students at this point, I'm going to go through the structure for ozone, which is O3. 4C students can skip over this, and at this point, probably even wrap up the video for C students, because the only content I have left to look at would be coordinate covalent bonds. Review the summary of drawing Lewis structures. Keep practicing the content here. That's, again, just for the 3U students would be that last paragraph really on coordinate covalent bonding. So we'll go back and look at some examples, and the assigned questions here on the last page should be your classwork for tomorrow. So number 3 we'll look at with 3U students, and 4C can sign off now. Has an ordinary covalent bond. Difficult concepts here, and I hope these examples were helpful. The assigned exercises, as you can see, for the 3Us, I suspect the number 2 also on page 82 is some coordinate covalent bonding. So we'll see you in class.